Well, I have to say it's a great honor to be here. As you mentioned, the work that we do in our group really crosses between a number of different disciplines and fields, between the basic science of how intelligence arises in the human mind and brain, and the engineering disciplines of trying to build machines that are smarter in more human-like ways. The work that I'm going to be talking about is really about the joint effort between those projects, but it's talking to a developmental audience, with the breadth that I think this community here that you've brought together around the world. To me, this is the most inspiring audience. This is what I think my true home is. I wish I really had better answers to the big questions that have occupied all of us, but I think we have some interesting steps that I hope will point the way towards where some of the answers might be found to really some of the most timeless questions in our field. This question of, as you might say, what do we start with and how do we learn the rest? Developmentalists have long talked about nature versus nurture in various forms. And I think all of us recognize that the truth and the really interesting answers are not any simple dichotomies, but rich, complex, interactive kinds of answers, which I think the tools of computation that our group has been trying to develop with a number of colleagues are starting to help illuminate. And I hope that all of us will see this as one of the ways forward towards addressing the biggest questions in our field. In the spirit of trying to bridge between the natural science and the engineering of intelligence, I think it's often helpful to start off from the AI side, because AI is so big these days. And yet, while I think AI is in all of our lives increasingly, and certainly in the news and the media and dominating many conversations, we have to recognize that we don't really have what any sort of true artificial intelligence in the sense of the original vision of the field. We have technologies that do things that we used to think only humans could do, and increasingly more and more of those. But we don't have anything like a flexible, general purpose, common sense intelligence that can learn for itself to do every one of these things as any one of you or us can do. So what's the gap? And it's that gap which motivates the work that I and my colleagues do. And there's many gaps between today's AI technologies and what we might think of as something really like a human-like intelligence in a machine. But one way to put the one that we've been focusing on is this. Today's AI technologies are especially enabled by machine learning, whether it's deep learning in neural networks or other kinds of machine learning. But really, these are great advances that have built up over a couple of decades in pattern recognition and function approximation. And you can't deny that that's useful technologically, and I'm sure an important part of how intelligence works in the human mind and brain and how we learn to be intelligent. And yet human intelligence is so much more than pattern recognition. In particular, it's about all the ways that we model the world, that we explain and understand what we see, not just finding patterns in our sense data, or our ability to imagine things that we could see but haven't yet. And then to set those things we imagine as goals, to plan sequences of actions which might achieve those goals, and then to solve the problems that come up along the way. Or from this point of view, we think about learning as building new models of the world, either refining, fixing our old models, or synthesizing whole new models as we experience more about the world, and learning from both our successes as well as our failures, and learning not just from our own experience, but socially and culturally by sharing our models with each other so that knowledge can grow across generations. So these are all the activities, I think, of human intelligence, and they are things which, from an AI point of view, we still don't have any machines that can do these kinds of things at technological scale, at even the ability of a young child, let alone a human adult. But imagine if we could get there, right? Imagine if we could build a machine that grows into intelligence the way a human does. That would be remarkable. It may not be the only way to build true artificial intelligence, but it could be our best bet, because if we think about it, it's the only example we have in the known universe of a system that learns to grow into full human intelligence starting from much less is a human child. So this case has inspired artificial intelligence researchers since the beginning of the field. For example, in Alan Turing's famous paper where he introduced the very idea of artificial intelligence and the famous imitation game, the Turing test, for probing it, he also suggested that the best strategy he could come up with for how to build a machine that could pass for a human intelligence is to build something that starts like a baby, and then you teach it like the way you teach a child. Because why would you do this? Well, presumably the child's brain is simpler, right? And that learning mechanisms could provide some scaling route. Of course, we don't know actually how children's brains work. Turing could only presume. In a famous line, he said, well, presumably the child's brain is something like a notebook as one buys it from the stationers, rather little mechanism and lots of blank sheets. Thus, building that would be the easier route than building the full adult level intelligence. Okay. But Turing was a brilliant guy, and he was also wise. He knew to put that word presumably in there. He knew he was only presuming. And if there's one thing that we've learned, or one general set of lessons we've learned over the last few decades of research in cognitive development, is that none of this is right. Namely, the human brain starts with a lot more structure than we might have thought, and learning mechanisms are much more sophisticated than just copying things down into your notebook, right? So there's no way I can do justice to all the developmental psychology that is behind these assertions, but I think this community knows, and many of you here have been the key contributors to that. I'll just highlight two kinds of ideas from developmental psychology that are inspiring and directly influential in the work I'm going to be talking about. One is the idea of aspects of common sense knowledge of the world that might be built into the brain from the very beginning. So I'm thinking of the work of Liz Spelke, who's my friend and colleague. We collaborate on some of the work I'm going to talk about here, but many others, such as Renee Bayer-Jean, Gary Gay Chibra, many who've studied the basic building blocks of common sense in the youngest infants. Or my colleague Rebecca Sachs, who studied these things both behaviorally and in neuroscience, showing with neuroimaging that even in babies as young as 3 months, much of the basic architecture of high-level perception, perceiving faces, bodies, places, these common sense targets of perception, are already there in ways that look very much like what we're going to see, or at least proto versions of what we're going to see in adult human beings. And then on the learning side, learning isn't, again, just like filtering through patterns and big data, but much more active, smarter kinds of processes. Here I'm referring to what you could call the child as scientist view, that Alison Gopnik and many others, Henry Wellman, Susan Carey, many others have developed, as well as the idea that learning, what we build are something like the theories of scientists, causal explanatory models of our data that support our planning. And the learning mechanisms are also something like the mechanisms of experimentation and theory revision that scientists might use. So here I'm pointing to the work of my colleague Laura Schultz, but many others who studied the learning mechanisms of children and the ways in which just playing around in the crib might be something like a scientist playing around in the lab, the source of our greatest discoveries. So the research that I'm going to talk about is how we can try to take these sorts of insights and capture them computationally. And that would be useful for building machines that could learn like humans and actually grow into human intelligence. But most deeply, it's because I'm looking for a computational reverse engineering account of how we actually grow into the full intelligence that we do. So the starting point for us will be the focus on core cognition. And most of the talk will be about how do we capture the basics of intuitive physics or intuitive psychology that you can see even in young children. So by intuitive psychology, I mean the sort of things you see in this 1.5-year-old here, or any others that we have around our house, playing with blocks, playing with the toys they can pick up and arrange, stacking up cups. And if you think about what has to be going on inside this kid's mind from an engineering point of view and compare it with the state of the art in robotics, which has made quite a lot of advances, right? There's still, in a sense, no comparison. The ability to not just manipulate the objects, but to form the plans that you can see this kid making, to debug the plans when they go wrong. As you can see here, his plan involved making a stack of those 2 cups in order to put that stack of 2 on the stack of 3 to make a taller stack of 5. But something goes a little bit wrong and doesn't go according to plan. There's another thing that goes wrong, but he figures it out, reacts accordingly, does things like move things out of the way without, quote, thinking. Of course, there's thinking that has to go on there. And just that process of envisioning, planning is, yes, it's worthy of applause from all of us. He's justly proud of himself. On the intuitive psychology side, I'll point to the famous experiments of Felix Warneken and Michael Tomasello. I saw Mike here, which is great. I'm sure these experiments need no review, but I'm sure you've watched these videos many times, all of you, but maybe watch it one more time or 2 more times and think about what has to be going on inside the mind of this 1.5-year-old, the participant in this experiment, who watches an action that, in a sense, he's never really seen before, although it has a lot in common with things he's seen, and is literally, in some sense, reading this guy's mind in order to figure out something about how to help him, right? He has to understand something about the physics of the environment, the constraints, as well as possible goals. And then when the adult stops, he goes and he does something which he thinks is helpful in a cooperative sense, right? My favorite part is when he steps back and just watch here in a moment and looks up and makes eye contact and then looks back down to the hands and what they're holding. It's as if, and I think more than as if, but it's as if just to showing us and maybe even to signal, I think I know what you're trying to do. And at least if I have that right expectation, then I know what, if I've understood your goal and I've done the right thing, then I think I know what you're going to do next with your body and your hands. Okay, so what we're trying to do here is to capture in computational terms the mental models inside these kids' heads that can underlie these common sensibilities. And then to say something about how they might be learned, how they might support learning, and how they themselves might be grown through learning. But I'm going to save most of the learning work for the end of the talk, because there's so much work to be done in trying to say what are the ingredients we need to capture these core notions of intuitive physics and intuitive psychology that builds on it. The pictures that I'm showing here, if you're familiar with graphical models like Bayesian networks, directed graphical models, you can think of these as sketches of such a model. Although, as I'll show you in a second, the actual technology we're going to use is a generalization of Bayesian networks called probabilistic programs. But what these are meant to be is sketches of the models inside the kid's head. So again, an understanding of the latent state of the world that gives rise to the sense data, like the images we see through some causal process, which you might describe with the means of graphics, and with some other causal process, what you might describe as physics, goes forward in time. And intuitive physics is about understanding and predicting what's going to happen and using that for your plans. And then intuitive psychology, you can think of building on that. This picture, again, this might seem like a sketch of some basic human mind architecture. This is not meant to be a scientific model of the human mind. It's meant to be a scientific model of the human's mind's model of a human mind. So a kind of core theory of mind, right? And understanding that the world has agents who can take actions that affect the physical state of the world as well as their own state. As a consequence of the world state and their own state, they have some process of perception which forms beliefs, some kind of representation of the state of the world and their own state, and then together with their goals, that leads to plans which lead to sequences of actions. And again, this is, I think, a reasonable model of many of the things that actual brains do, but it's intended here as a sketch of a computational model of the model inside this kid's heads, which he might use to understand what this guy is doing, or in a joint multi-agent sense, what we might be able to do together. Okay. So our goal, again, is to start off by capturing computationally, how could we build these kinds of things? And the way that I and my colleagues have been working towards this uses these ideas I mentioned a minute ago of what we call probabilistic programs and probabilistic programming. So think of this as a paradigm, a computational paradigm, which combines the best and most important features of more familiar paradigms that go back to the earliest days of our field, right? This includes neural networks for pattern recognition and function approximation. It also includes Bayesian or probabilistic inference in the reverse direction of causality. So using probability to be able to infer backwards to the causes of the sparse, uncertain data that you observe, the effects of those causes. And as Jochen mentioned, like that's a lot of what I've been known for and what a lot of my early work has been about. But what we've come to realize is that to really capture human common sense and how it grows, we need to combine these two ideas with what's really the oldest and best and most important idea of intelligence, which is the idea of symbolic languages for knowledge, representation, and reasoning. And these three ways of thinking about intelligence, as symbol manipulation, as probabilistic inference, as pattern recognition, function approximation in some form, they've fought it out over the years, but there's no need for that now that we have tools, computational tools, programming languages, and platforms that let us integrate the best of these motifs. So think of probabilistic programming languages as that, if you haven't heard of them. I'm highlighting here a number of these languages that have developed over the last decade or more. The ones in bold, Pyro, TensorFlow probability, Gen, are the most recent generation of what we'd call modern probabilistic programming languages, because they build on modern deep learning frameworks like TensorFlow or PyTorch, but they give you the power of probabilistic inference over symbolic representations. And especially, I want to highlight the GEN language, which was developed by my colleague, Vikash Mansinga, and his group at MIT, the Probabilistic Computing Group, which we've been increasingly using to build the kinds of models that I'm going to talk about here. Although most of the models that I'm going to talk about are a little bit older, haven't been built inside GEN, but it's a really powerful toolkit, which I would encourage people to check out. I'd also encourage people to check out the probmods.org webbook, which is a very gentle introduction with a lot of interactive examples using the web people probabilistic programming language that was built. This whole toolkit was built by Noah Goodman, and I contributed a little bit, and many others. So if you want to learn about these things for the first time, this is something we use in our undergraduate teaching and even teaching high school students. So these are a couple of resources if you'd like to learn more about these computational approaches. Now, there's one other important computational idea for thinking about these core systems, which is essentially, what are the programs that we're going to be doing probabilistic inference and learning over? I said these are generalizations of Bayesian networks. And if you're familiar with Bayesian networks, you think of something which captures, like the directed graph captures the flow of causality and captures both the unobserved and the observed variables. And the tools of Bayesian networks let you make inference from the observed ones back to the unobserved ones. Here you can think of the same kind of thing, but we have the power of a full programming language to capture causal processes like physics and mentalistic planning, which don't neatly fit into a graph structure. But what kind of programs do capture physics or planning? Well, here we take inspiration from, and also practical tools from, the field of game engines. So these days, game engines are increasingly used in many places outside the video game industry, which is where they were developed. But so many of you, I'm sure, are familiar with them. But if you're not, a game engine is a platform that allows a video game designer to make a rich, immersive, interactive experience for a player, often exploring or interacting in some three-dimensional world, without having to write everything from scratch. To focus on the story, maybe the characters, the world building, but not have to write all of computer graphics, or not have to write, for example, rich physical simulation, but gives you tools for rendering the world in real time with a lot of visual detail, a lot of increasing photorealism, but even for worlds that don't exist or maybe have never existed, maybe because their physics is somewhat different from the real world. You might be out in space, or at least out from the real world that most of us have been in. Or floating in some, zero gravity, or with portals that let you wormhole teleport, or all sorts of things that modern game engines can support. Physics in video games, well, I'd say both graphics and physics in video games are inspired very much by, like, our best understanding of, say, how light bounces off surfaces to make images and how objects bounce off each other. But it's designed often as a kind of a hack or fast approximation. It just has to look good on short timescales. It doesn't actually have to be fully realistic. So a game physics engine, for example, might be able to capture many kinds of situations like these, which are very complex if you want to actually get the physics right. Not just a few rigid bodies, but large numbers of rigid bodies, interacting in some complex way, like the ball and chain and blocks, or non-rigid things like the cloth draping over the sphere, or non-solid substances, fluids of various sorts. Okay. And again, the idea of a game physics engine is basically to simulate a wide range of things in a way that just looks pretty good over short time scales and can be interactive, and often run much faster than real time. Okay. Now, the way we use these kinds of models is not game style simulation engines have been used a lot in AI these days for training agents, especially in reinforcement learning, where you might train an agent with some policy in a simulator and then try to deploy it in the real world in a robot, and you face a so-called sim to real challenge because the simulator isn't exactly like the real world. In our model, the simulator is in the agent's head. There's also, of course, you could simulate the real world. But when we talk about the game engine in the head, we mean using these tools as the basis for the mental model inside, say, this kid's head, so that when they think about what's going to happen if I roll this ball towards the stack of blocks with the toy bird on it, well, maybe it'll fall over, maybe it'll fall over in this direction or that direction. Now, the simulator, as we said, is not actually right. It simplifies the real world and approximates in various ways. So the best you can do is make a good guess. And it's wrapping that kind of approximate simulation inside a framework for probabilistic inference, these probabilistic programming languages, that is the basis for how we're thinking about, say, common sense intuitive physics. Game engines also, by the way, have something called game AI, which is not real AI, but it's something kind of like the core intuitive physics picture I sketched a few moments ago, namely tools that let non-player characters in the game act in ways that are at least somewhat intelligent and adaptive and responsive to another player. For example, the guard of a base doesn't just like follow a fixed orbit around the base or shoot randomly into the air, but can perceive where the player is if the player is trying to, invade this base or something. Sorry that they're all often militaristic shooting games, but that's where the industry often has come from. But having a non-player character that can perceive, track, interact with, move towards, compete with, maybe even cooperate with the player character. So that means there has to be simple kinds of perception and planning models. And those also inspire the core intuitive psychology that we build. So just to illustrate how we might use this, for example, for intuitive physics, okay, we've, for a number of years now, going back almost 10 years, in work that started in our group with Peter Battaglia and Jess Hamrick, who are now both research scientists at DeepMind, the AI company, which I'm sure many people have heard of, and you'll see a number of folks from our group have gone to work on cognitive and neurally inspired AI there. But in work we started doing about 10 years ago, we took these simple blocks world scenes, think of like the blocks in the game Jenga, and asked people to make a number of different judgments about them. Most basically, given a stack of blocks, how stable is it? How likely is it to fall over? Now you might look at these stacks here, and probably you'd agree that the ones in the upper left look pretty stable. The ones in the lower right look like they're most likely to be falling over. So how do we capture that? Well, we build a probabilistic program like the one that's sketched here, where the outputs of the program are sequences of images, and underlying it are inputs to graphics programs which produce those images, but those world states are not visible. We have to infer them. And those world states are also the state of a physics simulation that can be used to predict forward. So just to illustrate what that looks like from a probabilistic programming point of view, we might have something like this. What I'm showing you here is one of these blocks images, and I'm showing you on the top this wireframe, which indicates a configuration of three-dimensional objects with certain size and shape, and there's also some physical parameters like density or weight that might be relevant, or surface friction, okay, which is the input to a graphics program that produces this image, okay? And perception here is in what's sometimes called inverse graphics, or sometimes also called analysis by synthesis. And the idea is that you're going to make a guess at the input to the causal process that would produce the data that you've seen. All right, I'm highlighting here a few references from Vikash Mansinga, the colleague I mentioned before, and Tejas Kulkarni. Things we did again a few years ago, which were some of the first probabilistic inverse graphics systems built on probabilistic programming languages. But I would encourage you, if you're interested on the perception side, to check out some of the latest work from Mansinga's group, which I don't have time to talk about here. But in particular, look at a recent NeurIPS paper from just the last NeurIPS conference called 3DP3, which stands for 3D perception with probabilistic programming, which is really taking this idea in a very exciting direction and deploying it in practical robotics contexts. But the basic idea is, again, to make a guess at the underlying world state. You can think of it as a kind of fast approximate Monte Carlo estimate, like a sample-based estimate of a Bayesian posterior over world states conditioned on images. Okay. This is one guess. Here's another possible guess. Okay. Those are just two different hypotheses about where the blocks might be that you might form in a quick glance at an image. Now, how we actually produce this, what are the algorithms? Well, there's a range of different algorithms, which I'm not going to go into, but these modern probabilistic programming platforms support both what you could call basically bottom-up neural network pattern recognition-based approaches, top-down kind of guess and check Monte Carlo, either importance sampling or MCMC type methods, if you're familiar with those, and most especially and interesting hybrids of those, which can be both fast and accurate. So that's all I'm going to say about how perception works, but it's one of the most exciting places where the neural network and the probabilistic inference over structured representations of scenes tools are coming together. Now, once we have a sample of the state of objects in the world, that's where physics comes in, because that same representation of objects, their shape, and a few basic physical properties, that's what the game style physics engine uses to make a prediction. And what I'm showing you here are a couple of time steps going forward of what the system would imagine how those blocks would move. Okay, this is propagating forward that first sampled posterior on world states. Here's propagating forward the second one. You can see these are a little bit different. The initial condition is a little bit different, but also then where it winds up after a few time steps. But importantly, it doesn't really matter whether you ran this simulation or this simulation for the level of intuitive physics. The precise positions of the blocks after a few time steps is very different, but all intuitive physics cares about is that most of the blocks fell over. So the way our models work is they run a small number of simulations like that, and then take some average or aggregate, and in this and then they use that to make a graded judgment of whatever parameters are of interest, such as the probability that or expected number of blocks would fall over. So this is a example of using such a model to model human judgments of stability. We in this experiment, which is one of the first ones that we run, but we've run many others like this. I'll show you one more experiment in a second, but in this very basic experiment, we showed people 60 different tower stimuli and had them judge on a scale of 1 to 7 how likely these things were to fall under gravity. You could also use a 2 alternative force choice judgment or any other ways, standard psychophysical judgments, and you get very similar results. So things which are high up on the y-axis are very unstable according to the model, or sorry, according to people. Things that are low down are very stable. And along the x-axis, I'm showing the average of a few simulations in this probabilistic physics engine, and and looking at the average proportion of the tower that falls. And you can see there's a pretty good correlation around 0.9. These particular 3 dots correspond to these 3 stimuli here. And I want to highlight one interesting alternative model, which is, you could call it like a ground truth baseline, or you could call it an ablation or a lesion of this model, because it's a very similar model, except it has no uncertainty. It's like a perfect physics simulation in this world with no uncertainty about where the blocks are or where what forces are in play. And what you can see when you run that model, which is shown here, is it's a much worse account of human judgments. So the y coordinates are the same and the error bars are the same, but there's no error bars on the x-axis anymore because there's no uncertainty. It's just reporting the percent of each tower that falls. I want to stress, this is a better model from a pure physics point of view. This is actually telling you the true number of blocks that fall, but it's a worse model from a cognitive point of view. The correlation is only about 0.6. And we take that as a sign that human intuitive physics is something like doing some kind of probabilistic approximate simulation as the model on the left. In particular, the ground truth model shows you that there are these stability illusions. Things like this, the red dot here, which corresponds to the stimulus, which is judged to be the most unstable stimulus in this experiment. And I think most of us would agree it looks very unstable. It's actually perfectly balanced. It actually it doesn't move at all under gravity. Okay, so that's why it's this big outlier here. And there's many other things of the same sort. All these points here correspond to stimuli which people judge to some degree are unstable, but actually they're perfectly stable. Nothing moves at all. Okay, but as the model shows, in some sense, they're generically unstable, right? If you have any uncertainty in where the blocks are, it should be falling over. And that's both, I think, how people's brains work, but also in particular how our model works. So it's a way in which this probabilistic simulation inference idea is able to capture something important, we think, about intuitive physics. Now, the same model, if all we wanted to do was build a model of blocks falling over, maybe that would be a little overkill. Okay, but the same model can answer really an endless number of different kinds of judgments or tasks that we could give to a person and that we could formulate as a query to our probabilistic programming engine. Okay. So in particular, we might ask, and we have asked people, well, if the blocks fall over, which way will they fall? Or how far will they fall? Or what would happen if we see blocks like these where there are 2 different color materials and some things are well, one color is much heavier than the other. Notice that the block geometries are the same, but by coloring them differently, it affects your judgment of which way they would fall. Okay? Or if I show you these scenes, which look surprisingly stable, can you infer that one color of material is much heavier than another? The same model can answer all of these questions, and even a question like this one, which if you haven't seen me give a talk about intuitive physics before, you've probably never answered exactly this question or performed exactly this task. Unlike, say, a question of, will something fall over, or how stable is it, or how heavy is something? We have a lot of experience since early childhood in making judgments like that. But the point of common sense, I think, and the point of having these kinds of mental models is that they can be deployed to answer questions or perform tasks that we never even thought of before until somebody or some experience raised the question. So consider this question. What if this table is bumped hard enough to knock some of the blocks onto the floor? Is it more likely to be red blocks or yellow blocks? Okay. So in this case, I think we'd all say red. There's many reasons why it could be red, but it's clear intuition. What about this case? Probably you'd say yellow. Here, red. Here, yellow. Here, yellow. Yellow. Maybe red in this case, yellow. Okay, so I'm sort of simulating what a typical person would do when they're shown these stimuli for the first time. Hopefully, if you're following along, you had similar intuitions. How did you come to those judgments? Well, the way our model does it is shown something like here. This is just a reconstruction inside the simulator of one of these configurations. And I'm showing you what happens when you give a small bump to the table. Now here I'm showing you the same reconstruction, but a big bump to the table. You might not have noticed that it was different, but again, watch this one. I'm just going to stop it after that. You see it's a small bump, and watch this one again. See, that's a larger bump. Okay. Now notice also, I could stop it after just a couple of time steps like I've done now, and you can already see what's going to happen. Okay. Namely, all the yellow blocks are going over and few or none of the red blocks. So for the purposes of our intuitive physics judgments, where we're just going to make a rough estimate of the expected number of blocks that land off the table, you don't have to run a long simulation. It would be probably intractable to run a long simulation, especially with any accuracy. But just a small number of time steps in a coarse approximate simulation with a fair amount of uncertainty about the force applied or other things about the initial condition. Just a couple of those simulations is enough to get a pretty good answer for intuitive physics. And that's what I'm showing here. Again, it's one of these plots where the y-axis shows the average human judgments of percent red or yellow landing on the floor. And the x-axis shows the average of a few simulations in this model. Okay. It doesn't fit quite as well as the model for the much more familiar which way will it fall judgment, but it fits almost as well. The correlation's about 0.8. And again, I think it's so striking that it fits almost as well for people's ability, capturing people's ability to make a judgment that before you've done this experiment, you've had no experience on this particular task. Okay, you've had lots of experience with physics, but in a sense, that's what the model's trying to capture is what is the generalizable understanding of objects in physics that can support very flexible kinds of reasoning. Now, the same kind of techniques can be used to capture intuitive psychology. I'm going to go much more quickly through this to make sure that I have some time to talk about learning. But I think it's absolutely central interest and some of the things that we're most interested in our lab and in our field. Here, the idea that we've pursued is to say, well, okay, what is, in a sense, the analog of basic Newtonian mechanics that you can approximate and simulate for agents? Well, it's something like what Julian Hara-Ettinger and colleagues called the naive utility calculus. The idea that, again, goes back to the beginnings of not just economic thinking, but any attempts to put math on human action and choice, which is that there's something like a notion of utility, positive and negative values that can be assigned to states of the world as well as to actions. And that a rational agent or any human-like agent tends to have goals, which you might describe as states, that if you can get to that state would give you some reward. But we understand that to do that, we have to take actions that can be costly. So the naive utility calculus says, well, think about the utility that comes from looking at the reward for achieving your goal state minus the cost of actions to get there, and take an action if the reward exceeds the cost. Or a sequence of costs, or choose the action which is, or a sequence of actions which optimize reward minus the costs you expect to incur. And this is a way to think about, of course, how you make choices and plans, but also in reverse, how you can understand the choices and plans that other people seem to be doing. So if this describes the causal process of choosing actions, okay, then Bayesian inference can work backwards to figure out, well, what somebody wants, what states they assign reward to, maybe also aspects of what actions they find costly. Julian and colleagues have explored many aspects of this. Julian was a student with us a few years ago. He's now an assistant professor at Yale, where he has taken these kinds of ideas and others in intuitive psychology in really amazing directions, far beyond what I'm showing you here. The same kinds of things can capture beliefs if we think about the intuitive analogs of expected utility, right? Where beliefs are like the probabilistic terms that lead to expected utility planning. I'm not going to go into that here, but in work that Julian did with Chris Baker and others, that's something that we've captured with these kind of models. So just to show what that looks like in simple kinds of physical action cases, because I think especially from thinking about where infants understand action, it's not in abstract spaces, but where agents are acting in the physical world, and the costs often come from physics, and the constraints come from physics, and the goals are getting objects into certain physical configurations, like putting the books on the shelf inside the cabinet. And to do that, you have to open the door to clear a path, right? So we might consider stripped down simplified versions of intuitive psychology on intuitive physics, where, say, for example, seeing this person here reaching for one of these objects in a 4x4 array, and we might say, well, what is her goal? And maybe right around now, you have a pretty strong sense that her goal is that second object on the second white object on the far left. At the beginning, right, you can't quite tell. You know it's not one of these red or green ones, but somewhere around now, you're pretty sure it's that white one. Now, if you were watching these dashed lines here, these lines on the right as I was talking, what you saw is right around the time, maybe around here or so, when you have a pretty strong sense of what her goal is, this dashed line went up here. That's the prediction of one of these Bayesian inverse planning models, a model which says we assume that she assigns a reward to one of these objects, one of the 16. She has costs of action, which can actually be determined by a physics engine. So we use something called the Mujoko physics engine, which was developed in robotics and now used a lot in reinforcement learning to calculate the physical cost of various trajectories for, say, a humanoid robot. And then we can work backwards to say, well, what given the actions that we took and the cost we can calculate on them, what do we think is the most likely source of reward, such that she would be pursuing the most efficient path to her reward minus the costs of action? And that gives rise to this Bayesian posterior, which captures reasonably well people's judgments of goals here. Now, again, if this is all we wanted to do, there are simpler ways to do it. Okay, but by having this inverse planning idea sitting on top of physics, we can use it to make sense of much more interesting kinds of action. So what happens if, for example, she's not just reaching from a standing position, but she starts from a sitting position? And then, by the time she's even just gotten up and moved over here, before she started to reach for anything, you can already rule out probably these white things, because if she was reaching for one of those, she wouldn't have even had to get up from the chair, or she would get up but move in this other direction. It's probably also a pretty good bet that she's going for one of these red or green things, because if she was going for one of the blue things, she might have already pivoted to turn towards it. Let's see which one it is. I always forget. Okay, it's that green one, right? But again, you have a pretty good idea which one she's reaching for. Even, well, okay, there she started to reach, but even like just when she's just starting to reach, you pretty much already know what she's going for. Now, of course, a lot of that, if you're paying attention to her eye gaze, that drives it. But as we've shown in some pilot experiments, if you block her head, you still have a pretty good sense just from how her body is moving. Or like in this scene, when she gets up and starts here, as soon as she just starts to step in this direction, you already know, even if you can't see her eyes, that she's probably headed for one of these white ones over here. Okay. Let's see which one it is. Oh, well, I was wrong. Okay, it was a good guess. You can see I'm not faking. I'm just giving you my own intuition. But again, it's you know that it's something that she has to have gone over here in order to reach for. Or think about this kind of scene here, where you're going to see somebody. This is, by the way, this work was all led by Tao Gao, who's this guy over here. Tao is now a professor at UCLA in several departments, including statistics and communication. but he also works with people in AI and psychology. And here you'll see Tao reaching in a somewhat unusual way. And you can see by the end which object he's reaching for. But even from the very beginning, like even say, let's say if I pause it around here, you already have a pretty good sense of which one he's reaching for. Now, if we were interactive, I would ask you, can you tell why he's reaching in this funny way? Probably a few of you can, but it seems like he's reaching over something, right? But you can't really see what he's reaching over. It's actually a piece of glass. It's an obstacle that is almost literally invisible, right? You can just barely see the edge of it here, but we still know it's there from how he acts, because people just don't reach in that awkward way unless they're reaching over something. So your ability here again is you're able to infer the goal of his action by assuming an efficient plan subject to his beliefs about the constraints. Okay, and it's more complex cases like this, which any one of these is very rare, but there's a long tail of human action that we need these kinds of models to understand, and that also includes in a multi-agent sense. Like if I see one person reaching here again over a piece of glass and somebody else helping them out, I can understand both what the person's goal is, the reacher, and the helper, that the person is trying to be helpful. I can also understand a scene like this, where I see somebody reaching and somebody else, well, not trying to be helpful, but the opposite, competing or hindering them, right? So what makes the scene on the top look like helping and the scene on the bottom look like hindering? Or what lets us look at this image sequence here and also understand that as helping? Well, we think these same kinds of models can be deployed in that setting, but now in a recursive multi-agent sense. So we have models of agents that do this kind of approximate rational belief desire planning, but where they can have beliefs and desires that reference their beliefs about another agent's beliefs and desires, or if you like, their expectations about another agent's expected utility. After all, what does it mean to help? Going back to things like the golden rule, there's helping is a very basic but also very abstract concept, which as in developmental psychology, Kylie Hamlin and many others, but in particular Kylie is one of the leading developmentalists to study infants' understanding of pro-social behavior. We've been fortunate to collaborate with her on some experiments testing out these kind of models with Tomer Ullman and colleagues. And as she and a number of others have shown, again, helping is a very abstract notion. Even young infants, in our study, 10-month-old infants, seem to understand that helping involves something like that, trying to do something that one agent thinks will, in some, qualitatively at least, provide reward to another agent. And it's not the particular action you do, but it's that abstract utility structure. And these kinds of models can start to capture that. All right. The studies with Kylie were not where they were inspired by a computational model, but they didn't quantitatively test it. And in a little bit of the developmental work that we've actually collaborated on here, I'll just highlight a couple of papers where we quantitatively tested the computational models that I'm talking about in young infants. So work with Erno Teglis and Luca Bonatti and others. Ed Vool was, who's now a professor at UC San Diego, but at the time he was a grad student working partly with me. We took these probabilistic intuitive physics models and used them to model the graded inferences of 12-month-old babies in these kind of dynamic object scenarios. So I'm not going to go into the details of the experiment, but the basic idea was that we showed infants scenes where there were 3 objects of one type and 1 object of another type. They moved for a couple of seconds inside. Sorry, show that video again. Okay, well, let's try this one more time. Okay, so you see the objects moving like this. After a brief period of motion, there's an occlusion. And then after either 0, 1, or 2 seconds of delay, one of the objects will come out. Okay, and across the experiment, we would vary the length of the delay, which of the objects, the rare or the common one, appears, and whether it was near or close to the exit, or near or far from the exit before the occlusion. In a probabilistic physics simulation, under pretty much any kind of dynamics that, any sort of Newtonian dynamics or any just smooth, spatially temporally continuous dynamics, that leads to a probability distribution of more or less expected outcomes. And what we showed in the experiment was that quantitatively predicted infants looking time. So it puts some mathematical meat on the idea of violation of expectation is actually saying, well, you look longer, the more unexpected things are. And in a sort of parallel line of work with Liz Spelke and Sherry Liu, Sherry was a PhD student in Spelke's lab who worked with Tomer Ullman on me on these studies. We looked at analogous kind of quantitative effects in these naive utility calculus type situations, where infants saw agents presented with possible goals and then various costly actions which varied in the cost of the action. It might be jumping over a barrier of a greater or lower height, as you saw here. Okay? Or it might be sliding up a ramp of more or less steep incline, or it might be jumping over a gap of more or less width. Okay? In each of these cases, the actions vary in cost, but the costs can all be calculated quantitatively in terms of how much work do you have to do in a physics sense, how much force do you have to apply over trajectory. And what Sherry showed really quite remarkably was that infants seem to be sensitive to this, that the more physical cost an agent was observed to be willing to exert, the more reward that the infants attributed to that agent in a relative sense, that the goal that the agent was trying to achieve was seen as more preferred. By looking at, I don't have the test trials here to show you, but by giving a trial where the agent now had an unconstrained choice of two possible goals and looking at which one the agent went to and whether there was, again, a violation of expectation if it went to the one that was inferred to be of lower reward. Okay. So these are just examples of how we can study these kinds of models quantitatively in young infants. But if we're interested in developing minds, what we really want to know is, where does learning come into the picture, and how do you learn with and in and around these kinds of common sense ideas? And I left myself only about 10 minutes to talk about learning, but that's I feel that you can't really study learning unless you know what you're trying to learn. And I'm very excited that these days in our group, what I've talked with you about is work that we did over the last, starting 10 years ago and over the last really 3-4 years on the intuitive psychology side. But now we're really excited to get back to learning. And there are different ways you could approach these common sense core ideas. You could think of them as the targets for a more sort of blank slate style learning. And a lot of people in AI have been pursuing this, right? There's sort of an ethos in certain parts of learning-based AI, deep reinforcement learning, that say either philosophically or some people argue that it's just a better way to build systems, that you should build in as little as possible and learn everything from scratch in some end-to-end way. Okay. As an example of how one might do that, I'll point to some work by some colleagues of mine. This is Nick Haber and Dan Yeamans. All of these researchers are at Stanford. Damien Rauka, Fei-Fei Li were also key contributors. We work with these guys on cognitive development these days, not on this paper. This is something that they did prior to our interactions. And they built an agent which had a kind of self-supervised kind of curiosity-driven loss. There's a lot of other interesting related things that have been done in AI by, for example, people like Deepak Pathak, Pulkit Agrawal, who were at Berkeley at the time, or Pierre-Yves Oudéa's group in developmental robotics. So I think this might be familiar to many of you. And what they showed is that an infant kind of interacting with objects in a realistically simulated physical environment can start off having no notion of object, with enough experience, get something that basically looks like a kind of object-based attention. Okay. I think that's an interesting demonstration of that, but I don't think it's really how it works with infants. I think there's plenty of good evidence that our brains are built from the very beginning with some kind of representation of the world as not just being features and pixels, but actually having objects there. So the work we've been trying to do is to say, well, what if you build in the basics of something like a physics engine or a game engine? Then how can you learn with that? How could you learn on top of the game engine, or how could you learn inside the game engine, or even how could you learn the engine itself, maybe over developmental time, or maybe also over evolutionary time? And then how could you use that as the foundations for everything else that comes from cultural learning once you have intuitive psychology sitting on top of it and language that builds on top of that? So this is really the roadmap of where we're going. And there's a number of ways we've worked on this. So in some sense, one of the things we have good reason to believe that people learn, even if all of intuitive physics were innate, which I'm not saying it is by any means, but even if it was, that's not enough to actually learn how to accomplish goals. And learning how to use objects as tools, or just in general, how to manipulate the physical world to achieve your goals, is very manifestly something that humans do both individually and culturally. And you see a lot of development over the first few years of life like that. So one way we've geared up to do that is developing basically paradigms where we can study flexible physical problem solving and tool use and learning in that context. And here I'm pointing to work by Kelsey Allen and Kevin Smith. It was recently published in PNAS, and there's a couple of follow-up papers that are working their way through publication. But the inspiration for us here was to think about flexible physical problem solving and tool use. Like if you've gone camping and you find that you left your tent stake hammer at home, what are you going to do? Well, you might look around and see some objects that could possibly be used to hammer in a tent stake into the hard ground. Several of these you might rule out right away based on their visual appearance, but others you might have to try out, and there might be a little bit of trial and error. For example, you might try using this rock, but when maybe you're not getting enough leverage from that, you might look around, look for a rock that's sort of a little bit more hammer-like. Again, it doesn't really look like a hammer, but it could be used as one. So we built this basically a video game inspired by some of the kinds of physics games which are popular to play on smartphones or touchpad devices. We call this the virtual tools game. And you can see examples of people playing this game here, where it's very simple, deceptively simple maybe. You choose an object from this palette on the right, that's your tool. And then your only action is just to drop it into the scene. So you plunk it down there and let go, and then physics starts to run. Your goal is to get the red object into the green region by the end of the trial. Black things don't move, but any blue or red object moves. And sometimes what you have to do, like up here, is realize, watch this one again, that in order to solve the problem, you have to block that blue thing, because that blue thing is going to block your red thing. So you have to block the blocker. Okay. You can see down here on the left, there's a kind of catapulting thing. Well, initially, somebody doesn't quite realize that. They try to bump this thing down the platform, but then after a little bit of time, they realize, okay, well, that's not going to work. So let me switch to a different strategy, this catapulting idea. Ooh, but that wasn't quite right. But notice they realized it was almost right. They just have to get more force, which they have to drop the thing from higher, and now they've solved the problem. So you can just see a sample of some of the kinds of problem-solving situations that this game puts out, and some of the strategies that people come to. We've built a model for how you can do what is a kind of learning to use your intuitive physics engine. It's trial and error learning. You saw people making errors and learning from the right there, but it's a very rapid kind of trial and error learning, right? And I think this is most actual trial and error learning that humans do is not like millions of trials of reinforcement learning, but this much more rapid kind of debugging of a plan. Okay. Which can include realizing that what you thought would work just doesn't work, and you have to do some random exploration. So the way this model works is it starts off with it's called the SUP, or sample simulate update model. It starts off with a prior on where you might start to use a tool, just based on some basic notions of affordances, like basically choose an object and drop it somewhere where it's likely to contact and exert force on something. That's a very weak prior. Then you try the model says, try some mental simulations, try out a few things like that, and see if any of them look like they're going to work in your approximate probabilistic mental physics engine. If one of them does work, try it out in the real world. If it does work, you're done. If it doesn't work, try to learn from your mistake. Basically, use some feedback from that to update your prior, and then just repeat. So the model has effectively two loops, an inner loop of mental simulation and then an outer loop of trying things in the world. We can compare the outer loop behavior with people's behavior. We can't look inside the head and see your mental simulation, but we can see what you actually tried and how many times you had to try things in the real world to succeed. And the model captures people's learning curves of like basically these are cumulative probability of success as a number of trials. So it's like the rapid trial and error learning curves in a number of these different levels. And it can also capture both the first placement that people try, essentially the prior, but also what they do at the end, like their last action, what eventually solves the problem, which is not every, there are ways to solve the problems that people never find because they're a little bit weird, and the model also doesn't typically find them. Now, this is, again, this is just the simplest kind of learning you might do on top of a probabilistic proximate simulator for core physics. There's more interesting kinds of abstract things that get symbolic. Like if you want to learn the concept of a catapult that can generalize across, all the different ways that you might catapult a person into a lake, a rolled up crumpled piece of paper into the wastebasket, or even in this game, how do you do that? Well, the way first of all, in our experiment, we've shown people can learn these strategies over a couple of different related levels. So it's no longer just learning within a level, but it's learning like across related levels. And they can transfer to very different situations that would be solved with the same kind of abstract strategy, catapulting, let's say. And we can capture that by replacing the prior with a simple set of symbolic rules which capture this abstract strategy. So we have this probabilistic grammar that specifies objects, attributes, and dynamic, either spatial or dynamic relations between objects, and that abstractly can describe a strategy. Like here's the strategy in that grammar for catapulting. Pick a large tool, choose a wide object beneath the ball, and place the tool high up and to the right of the wide object. So that's the description in English, and these are the descriptions in this mathematical language. And the system is able to synthesize that kind of abstract strategy from a little bit of experience, from a few examples it can generalize in that way. Okay. So again, this is just a step towards one kind of important learning that you do on top of your core intuitive physics. But we also, of course, want to actually learn physics. So that could include learning physical parameters. Like, for example, in this work that Tomer Ullmann did a few years ago, and I think actually the date should be 2018. Sorry, this was published in Cognitive Psychology ultimately in 2018. We showed people these brief scenes of, like, think of it as like air hockey tables with funny physics, where there were forces, mysterious forces of attraction or repulsion. Some objects might be heavier or lighter, friction might be greater or less, and people can make judgments about these underlying physical parameters, which you can capture as something like hierarchical Bayesian inference in a physics engine program. So it's like you take the physics simulator, but now you're uncertain over some of the parameters, over the masses or the friction coefficients, the things that we just assumed we knew before. But now you do Bayesian inference over those from seeing how the movie unfolds. Or you might even be uncertain about which force laws are in play. Now that's a good start, but that isn't going to be enough to actually build a whole physics engine. So that's like, again, if you have the physics engine, but you don't know some of the parameters. But what if you actually wanted to learn a physics simulator or capture what might be, more sort of deeper, longer term developmental trends? So here I'm pointing to the work of René Baillargeon, who has done more than anyone to map out and suggest, even with, I think, very big error bars, everybody would agree, but to map out and suggest something like a developmental timeline of, say, how intuitive physics develops, and mapping out when certain concepts of, let's say, stability, support, gravity, inertia, mass and weight, center of mass sort of ideas, when they become available to a child. We might hypothesize that maybe what's going on here is some kind of development of a series of increasingly sophisticated physics simulation type engines or something like that. So what we have been very interested in, and we're just starting to make some of the first steps towards, is could we capture the starting state with some kind of proto-physics engine, and then try to say something about the developmental time course of how learning from experience, both observation and interaction, would refine and grow that physics engine in the head. Tomer Ullmann, whose name I've mentioned a number of times, I'm not sure if I mentioned, he's now an assistant professor at Harvard. He really mapped out this idea in a very nice way in a Trends in Cognitive Science article a couple of years ago called Mind Games. And together we had a chapter in last year's annual review of developmental psychology, or I guess, well, 2020, so now it would be the year before last. So you might check out the chapter, which is called Bayesian Models of Conceptual Development, but it kind of gives you an overview of early work that we did on using this idea of hierarchical Bayesian inference, like I showed you, up to this more recent stuff, which I'm just going to end on here. The challenge that we try to address in that annual review of developmental psychology chapter is what we have called the hard problem of learning, right? And we call it that because it's in contrast with the problems of learning in a neural network. Like, why have neural networks been so influential in engineering? They have a kind of scalability that lets you make them incredibly big and have the same simple learning algorithm, gradient descent, which if you're willing to wait long enough and give it enough data, will find a good solution. Okay. But if you're taking this approach where you're capturing your knowledge with something like a physics simulation program or any kind of symbolic program, okay, or probabilistic program, it's the search problem is much harder. Search in the space of programs, you don't have anything like the nice geometry with some kind of smoothness that you can exploit with gradient descent. But somehow children solve this much harder search problem. Somehow, through some combination of development, or sorry, their own experiential learning, but also surely a lot of linguistically and other kinds of culturally bootstrapped learning, are able to come to really remarkable mental models of the world. So how could this work? Well, the general idea that we've started to develop, and this is another recent Trends in Cognitive Science paper, that's not about intuitive physics. This is about the general idea of what you could call learning as programming, or we called it the child as hacker. And this is based on the thesis work of Josh Rule, who finished again in just recently in 2020, and is now a postdoc with C. Piantadosi at Berkeley. This was a joint kind of white paper that we wrote together, where we sort of tried to develop this general idea that programs, such as the ones I've talked about, but much more generally, can be thought of as our best universal representation for all the different kinds of knowledge that a human builds over their lifetime. And here we're just channeling Turing effectively, like the idea of Turing complete languages of thought, whether, in all these domains of human expertise, not just physics, that's really our best and arguably only universal representation language. But if knowledge is some kind of program or libraries and languages of programming, then learning has to be all the ways of making code better. And we draw inspiration here, or suggest that developmental psychology should draw inspiration from all the activities that you do when you're programming, or as we like to say it, MIT has this, and others in programming have this notion of hacking, which isn't the bad guy hacker who breaks into your email and steals your credit card numbers, right? But hackers as like creative explorers in the world of code. Okay. So think about all the things that you do when you're hacking on your code to make it better. That might include tuning parameters in existing functions, but most of what you do is actually modifying the code in some more fundamental way, like debugging a function, writing a new function, a new symbolic expression. It might mean writing libraries of functions, or refactoring code to make it more reusable, or even writing whole new languages. And we think it's all these activities that go especially beyond, there's writing a function, like writing a little mini program, building a bigger program, but writing what are effectively libraries and languages for programming that can capture, in this metaphor, some of the most interesting kinds of cognitive development, where we say like building an intuitive theory. It's a whole way of thinking, or a domain-specific language of thought. Now, we don't yet have computational models that can do that, but we've started to take some small steps. This is the last little research nugget I'll leave you with, this is an AI model that was developed by Kevin Ellis, also a recent graduate from our group. And it's with a number of other colleagues, especially Kathy Wong. The system is called Dreamcoder, and you can read about it on arXiv. I don't have the date here, but there's a 2020 arXiv paper, as well as a PLDI paper, which probably most people in this community don't know, but PLDI is a programming languages conference. And this paper is really interesting because it combines ideas from multiple aspects of probabilistic inference and learning with ideas from the field of programming languages. What the system is really doing is it's learning to build its own programming languages. We give it problems to solve in a number of different domains. Here I'm showing 8 different domains, where every domain consists of a bunch of basically small problems, each of which can be solved by writing a program. And what the system does is it learns to solve each individual problem, but it also learns to grow its programming language and its strategies for using that programming language so that it can more effectively and efficiently solve more problems. And it has a really nice kind of bootstrapping loop, which involves a kind of wake-sleep learning that, if you're familiar with wake-sleep learning in neural networks, it's a similar kind of idea in code. So in the wake phase, the system is given some inputs and it writes a short program to try to solve that problem. In the sleep phase, there's sort of two sleep phases. In one, which is kind of very loosely inspired by like slow wave sleep, it forms abstractions by compressing out common motifs in the code that it's written for problems it's solved in its waking phase. And in the dreamlike phase, similar to like the wake sleep algorithm in the Helmholtz machine, if you're familiar with that from Jeff Hinton, Peter Diane and colleagues, or any other kind of wake sleep learning, the system dreams or makes up problems to solve. So it sort of imagines new problems to solve for itself. And these are problems because it made them up. It knows the answer. And so it has training data for, in this case, a neural network that is trained to basically find useful paths through the solution space of programs. So the neural network looks at the data that specifies the problem, and it suggests, using pattern recognition techniques, what might be useful programming language components like primitives, commands to use, what would be next useful in writing that code, basically. So it guides the search through the space of programs. It takes that really rough topology of the search landscape that I showed a few slides ago and smooths it out effectively, learning from experience. So this is one of my favorite recent pieces of work because of how it combines all these motifs. The basic knowledge is symbolic code, but this idea of like forming a library that's compressive and that helps you write programs more compactly, that's actually a kind of hierarchical Bayesian learning of the prior, and which is what this programming language is. And there's also a neural network and some sort of procedural expertise that's captured through its pattern recognition system that is used to learn to guide the search, but actually mostly from self-generated simulated data from the internal probabilistic model. So just to illustrate kind of what that does, for example, consider a domain of drawing problems where the problems here there's some building tasks and some drawing tasks. Like, so if you know the programming language Logo, where you have turtle graphics, it's a way that many people, at least in my generation, learn to code. It's still a good way to learn some basics of geometry and recursive functions. The system is given the task of writing programs that can produce all these drawings here. And it starts off with very minimal tools. It just has a pen that it can put down and lift up, and a turtle can move forward and it can rotate some angle, so it can kind of turn. And then it has recursive functions. So you could in principle kind of write anything, basically. It's a Turing-complete language. But it's very hard just with those primitives to write programs that would even produce these even slightly complex drawings. It's not that hard to write a program that draws a circle or a straight line. And in the first stages of learning, that's all this system can do. But then over time, it builds up a library of these programming components like spirals, circles, polygons, and then higher order functions that say express radial symmetry that repeat these elements. This is just an illustration in a sense of what you could think of as a different kind of deep learning. It's a deep library of functions. So it starts with some very minimal initial functions and then basically weaves these into some higher order functions, so that by the time it's built up this whole library with its interdependencies, now you can give it these complex drawings and it can write very simple, short programs that draw these things, but they don't use the original primitives. They use these things like function 8 or function 5 and so on. These, or function 16, these are these new synthesized primitives that it didn't have at the beginning, and it needs them. It needs to have built them before it can write short programs to solve these problems. Maybe the neatest way to see what's going on inside its head is to look at its dreams, to look at the beginning of learning when it just makes up problems to solve for itself. They're not very interesting because it has very few primitives in its language. But over time, after it's built up its language, its dreams get much more interesting because it's built up a whole probabilistic model for what things look like in this domain. And you can see both how that expresses the concepts that it's come up with, why now it could solve many more problems with a short findable solution, but also why this would be much more useful training data for training a pattern recognition system to guide the search from the kinds of drawings it's actually going to see. So you can apply the same kind of thing actually to learning physics. I'm not going to go into that, but it's quite general. You could learn how to, the system we show can be used to learn physics equations from the kind of problems you have in intro physics, or learn how to sort lists and learn sort of modern recursive functional programming. And though we've far from actually achieved this goal, we think this is the sort of thing that can be used to actually get us beyond that core knowledge state of just learning physics or learning about planning and inverse planning, to learning language and all the things that people learn once they have language. So once you can basically write code and learn to write languages of code, then it's not that hard with recent tools to be able to map natural language onto those internal languages of thought. And then that gives you the ability to learn from all the things that humans do, whether it's from spoken language or written language. So that's where I'll leave you. I know I went a little bit longer, but I guess development is a big project. But I'll just leave you with this roadmap of what we've done and where I think we're going, to try to fulfill what AI researchers would say has been the oldest dream of their field. But from the standpoint of cognitive development, I think that's the most interesting thing, is to understand how we start and where our minds come from. And that includes that from a computational point of view, that means getting the tools to capture both the starting state and the learning algorithms, these ideas of like probabilistic approximate inference on simulation engines, and these tools for basically learning as programming that can extend, build on, and take us beyond that, and bootstrap new languages, and even give us the tools to get the real singularity, which is once natural language and all the full power of human culture that enables. Okay, so that's where I think we're headed, and I'd be happy to take any questions, and I'd love to hear from people, even if not in the session, who have related ideas or very different ideas about how to move us forward. Thanks.